All right, this is my first attempt at an explanation video. In this video, I'm going to explain the first full stoichiometry practice that we'll be doing in class. We're doing this in class on February 10th, Monday, February 10th. The reason that we're doing this practice and we're learning stoichiometry is because this is the real chemistry that scientists have to do all of the time. We'll be doing an experiment ourselves this week using this math. We'll also be taking our next unit test next week. So it's really important that we learn each of these steps to completing these pretty complicated problems. This problem is one from real life. This is something that NASA scientists actually had to think about and solve. The carbon dioxide that is exhaled by astronauts is actually captured and converted into water by reacting it with lithium hydroxide. In the space shuttle, they have this lithium hydroxide scrubber, which cleans the exhaled carbon dioxide from the air. The gas goes in through this inlet, it reacts with the lithium hydroxide and produces two products. Those products are, as seen in this chemical reaction, lithium carbonate and water. Water is a really useful product on a spaceship because we only have how much water we bring with us on a spaceship, right? So this was a super useful piece of chemistry knowledge for the scientists and engineers to know and to implement on this spaceship. We are going to do the exact same type of problem that those NASA engineers had to do. The first step in solving this type of problem is balancing the chemical reaction to see what actually goes on here. In this chemical reaction, we can balance it using the same method that we have before, where we write out the reaction, we write out all of the reactant and product elements, and we balance it from there. I'm not going to spend a ton of time on this. Just to show you quickly, you can pause here and figure out how I found that there needs to be a coefficient of 2 for this lithium hydroxide. So we're going to go from there with our balanced chemical reaction. We have 1 mole of carbon dioxide reacts with 2 moles of lithium hydroxide, which gives us 1 mole of lithium carbonate and 1 mole of water. The next piece of information we need to know going into this type of problem are the molar masses of each of these molecules. We've calculated molar mass before. This is a process where you take the molecule, for instance CO2, and you break it down into its respective elements. We have carbon and oxygen. You use the periodic table to look up the mass. Looking at the periodic table, we need to find the mass of carbon, which is the bottom number here on the periodic table. We find that it's 12.01. And if I look at my chemical formula, I see that there's only 1 carbon atom here. So I'm going to multiply by 1 for that 1 carbon atom. Oxygen, again, look at your periodic table, 16.00 times the number of oxygen atoms in this molecule, which here is only 2, times 2. 12.01. And 16 times 2, if you plug that in your calculator, you get 32.00. The last step is to add these products together. And we find that for carbon dioxide, the molar mass is 44.01 grams per mole. If you repeat this same process for the other molecules in this balanced chemical equation, you'll find the following amounts. Lithium hydroxide should be 23.95 grams per mole. The first product, lithium carbonate, 73.89 grams per mole. And the second product, water, 18.02 grams per mole. So again, these are the molar masses of each of these compounds. We'll see soon why we needed to calculate those molar masses. All right, so getting into the actual stoichiometry problem. in order for NASA scientists to be fully prepared for a space shuttle launch, they had to figure out how much carbon dioxide does an astronaut exhale and how much water can we produce from that. So they did some measurements and found that each astronaut or each person exhales about 1 kilogram of carbon dioxide per day, which, if you do the unit conversion, is 1,000 grams of carbon dioxide. What we need to find out is how many grams of water can be recovered each day from each astronaut. Solving a problem like this, going from grams of one molecule to grams of another molecule, involves 3 steps. We've done each of these steps before. It just might feel like a lot because it's 3 steps all together to solve one problem. The very first step, if we break this kind of problem down, is we need to convert to the universal language of chemistry. We can't go straight from grams of one molecule to grams of another molecule. That's because all molecules have different molar masses. Those molar masses are the relationship between grams and moles of that particular molecule. So we first need to take this grams of carbon dioxide and convert it to moles. So step 1 says, calculate the moles of reactant, carbon dioxide, by converting grams to moles using molar mass. We'll set this up just like every other problem that we've done in this unit. We start with the given, and we multiply by a conversion factor. In this problem, we were given 1,000 grams of carbon dioxide. That represents how much carbon dioxide is exhaled by the astronaut each day. We need to convert this to moles, which means grams is the unit we're getting rid of. It needs to go on the bottom. The unit of the given goes on the bottom. And we need to get to moles of carbon dioxide. This conversion factor, like stated in the problem, is the molar mass of carbon dioxide, which we calculated here. A little hint to figure out where this number should go is when you look at the molar mass number and unit, grams comes first. That is your hint to say that the number for the molar mass should go next to grams. And this is how many grams per 1 mole. So that's why we get 1 mole on the top. Remember, you can pause this video at any time if I'm going too fast. So in our calculator, we need to put 1,000 grams times 1 divided by 44.01, which is mathematically the same as just ignoring this one and doing 1,000 divided by 44.01. You can solve it either way. So I'll type 1,000 times 1 divided by 44.01 in my calculator. I'm making sure to use parentheses for these multi-step problems so the calculator does not get confused. And we get a long answer with many decimals afterwards. Long story short, we can actually cut this number off at the same number of decimal places that we see in our other number. So I'm just going to keep 22.72 for this answer. I'm going to keep my color, 22.72 moles of carbon dioxide. What this means, what this really means, it's the same exact number as this 1,000 grams of carbon dioxide. It's just in a different unit. We just converted the grams to moles, all right? So it's the same thing, just in a different, more useful unit. The next step is we're going to figure out how many moles of water you can actually make from this amount of carbon dioxide. So if we react this much carbon dioxide with that lithium hydroxide, how much water are we going to get? The way we do that is convert moles of reactant, which we just found, to moles of product. In this case, we care about the water product. We're going to do that using the molar ratio. The molar ratio, again, is the number of moles of each of these molecules as seen in the balanced chemical reaction. So this coefficient actually means 1 mole, 2 moles, 1 mole, 1 mole. So in this reaction, for every mole of carbon dioxide that is used, 1 mole of water is created, is the product. So let's see what that looks like in our step-by-step math so that we can follow this for any problem. We start again with the moles of reactant, 22.72 moles of carbon dioxide. We're going to multiply that by a conversion factor, just like every other problem we've solved in this class. Given times conversion factor. They tell me the conversion factor to use is the molar ratio. I'm going to make sure that I have the same unit as my given here in the bottom so that they cancel out, moles CO2. And what I want to end up with at the end is moles of product, or mole H2O. Okay? And I look again up here in the balanced chemical reaction and I see that it's 1 mole of carbon dioxide for every 1 mole of water. So that's where I got those ones. Then this is a pretty easy problem to solve. Anything times 1 is just itself. So we're going to get the same exact number, 22.72 moles. But this time, moles CO2 cancels. So we have moles of water left. So in this step, we've essentially solved the problem. We know how much water is produced based on a certain amount of CO2. But mole is not a super useful or convenient unit for us to think about. So the very last step in solving a problem like this is we're going to convert to a more useful unit. We'll convert to grams. Knowing how many grams of water is produced is a little more useful than moles. So on the next page, we'll do step 3 of this problem. Convert moles of product produced to grams of water produced using the molar mass of water. All right, moles to grams. Again, we just did that before where we went from grams to moles. Now we're going to go from moles to grams of a different molecule. All right, so now we start with our product from the last problem, 22.72 moles of water times a conversion factor. This time we'll use the molar mass of water. We're trying to get rid of moles, so it goes on the bottom. And we're trying to get to grams of water produced. If I look on the previous page, I see that my molar mass of water was 18.02 grams per mole. 18.02 grams per 1 mole. The very last step, the last thing we need to do is type this into the calculator. 22.72 times 18.02. And we get our final answer, which is 409.4. The moles and moles have canceled, so I'm left with my final unit of grams of H2O. To put this answer into a little bit of context, a gram of water is the same as 1 milliliter of water at most temperatures. So this is almost 500 milliliters, which is the same volume as a regular bottle of water. This is 500 milliliters. So these astronauts, just by exhaling and having this machine capture that carbon dioxide, are producing almost a whole water bottle full of water every single day. That's it. We just did our first stoichiometry problem from start to finish.